I thought they used to just go straight.
Is it good? All right. So hopefully. All right. Okay, so we were looking at systems of linear differential equations. We're going to have just a system of two differential equations. Our x and y are unknowns, and we have equations that describe their derivatives, but they are coupled because dx over dt depends on the solution x as well as the solution y, and the y might in general depend on x and y as well. And we translated this system of differential equations into matrix vector form. The coefficient matrix is this purple thing. The solution vector is unknowns are x and y. We can solution vector on the right-hand side. If you remember, matrix multiplication will end up being a times x plus b times y on the first row, and then c times x plus d plus y on the second row. So this actually does translate to the right-hand side we see here. The left-hand side, dx over dt and dy over dt, can be also consolidated into a single vector dx over dt over dx dy over dt as a differential operator, d of dt, and then you just have x, y, so it's like the derivative is acting on this vector, but we just said that x, y can be further shorthanded as the vector x, so it's a way of writing this system. Okay, so then we said, what do you think are the solutions x and y that will have any hope of making these two differential equations that would have any hope of, when you plug it into these two differential equations, it would basically e to the something t, e to the lambda t is what I said. I mean, in the past we used r, e to the rt or something, but we're just going to use lambda for this because it's the convention they like to use for systems of equations. So the idea is that if both x and y are e to the lambda t, then the derivative will also contain e to the lambda t for x, and the derivative for y will also be e to lambda t, and then all the x's and y's also have e to lambda t. So then you'll have a bunch of terms on the left that e to lambda t, and then you have on the right, on the left, you have e to lambda t. So you've got a bunch of terms that are resembling each other. You just have to make sure that the constant, so there's a u and this v. In the past, maybe we used like, capital A or capital B or whatever. But right now, we're just going to use u and v. These u and v are constants. So we're saying like we're going to come up with some constants that we need to find in front of this solution, these solutions that will end up giving us all the terms on the left and the right match. So I'll say that the lambdas for both of these have to be the same, because if you use the different lambda for both your x and y, and of course when you look at the right hand side, both those exponentials to be the same, because if you had like e to the 2t and then e to the 3t, those don't add up to give you e to the, so if x was e to the 2t, then the derivative would be to the 2t. So you do need this x and y to be the same exponential. So these are the same lambda. Okay, so we have three things we need. U and v are constants. So we have x of t is going to be some constant times e to the lambda t. Y is some constant. V, something different. We're not going to assume that the constants that multiply the x and the y are the same. They may turn out to be the same. We don't assume that ahead of time. But the lambdas on these exponentials better be the same, because that's the only way you're going to get this right-hand side to have two exponentials that are the same, adding up together. So that's basically this paragraph explaining why we should expect this to be the right solution form. But we have three unknowns. We have u, v, and lambda. So we're going to try to find those three unknowns. the idea is that we should be able to plug these, like we've always done in the past, into our differential equation. Well, in this case, two differential equations, because you have a system of two equations. And we're going to find u, v, and lambda that will force this to satisfy the system of differential equations. You're probably going to be like, well, we have three unknowns and only two equations to plug in. So you might think, oh, maybe there isn't enough equations for the unknowns, the number of unknowns we have, but we'll see that it works out. So what I'll do is I'll copy this, well, why don't I write the solution vector? So what we're saying, so this is like the solution vector, xy, right? So we have that. And then we're making the proposal that exponential. So it's going to be like the x is going to be u, e to the lambda t, and then y is going to be v, e to the lambda t. So we're making that, proposal that the solution consists of these two solutions. And some people like to write this out as, since there is e to the lambda t that's common between those two, we can pull that factor that out of the vector. And then we're left with u and v. Okay. And then I'm just going to redefine this as shorthand this as the uv vector, similar to how we said the xy vector is the x vector. I'm going to call this the v vector. For vector. And then that makes this condensed to et. So this is using, again, right? We just said that this is the proposed solution, and we're just going to say, the solution is going to be that. So this equality here comes from this proposal. Now, the other thing is the derivative, dx over dt. This dx over dt, let's write that out given our, this is like plugging it into the, x and y, but also into its derivatives. So we should now be able to use these proposed solution forms to find what is dx over dt. Dx over dt is, again, a condensed way of writing dx over dt. Dx of the vector is this condensed way of writing this. But given our x and y are equal to these right here. So then you're just going to say, what is dx over dt? Dx over dt is like taking this derivative with respect to t. Lambda and u are all constants, so it's just going to be u. Well, it's going to be u, and the lambda pops out because of the chain rule, e to the lambda t. Let's do the same thing is going to be here. It's going to be v lambda e to the lambda t. We're just plugging in the proposed solution for x and y, and then into the x and y, as well as into its derivatives. That's how we've always plugged it into our differential equations. We just have two differential equations we're plugging it into. And again, for this one, there is something common. There is a lambda e to the lambda t that's common between both of these. So you can factor that out, and then you'll just have uv. When it's written like this and there's a number or some kind of expression in the front, the idea this means that it's equivalent to multiplying these component wise, each of these u's and the v's. And we just said that this is equal to we could shorthand this as vector v. Right, so then this shorthands to lambda e to the lambda t vector v. Okay. Another way you could have done this, we did it like this right here, but another way is if you wanted to, you could have just went directly from this to here. If you think about this, this is our vector x. So if we just took the derivative of this vector x with respect to t, then it's like saying the vector v is not a function of t. Vector v is a vector with u and v as its components, and u and v are both constants. E to the lambda t is the only thing that's a function of t. So what you'll be left with is if you went from here and took the derivative with respect to t directly, The vector v is a vector of constants, so that stays. And then e to the lambda t, that derivative would be lambda e to the lambda t. So you could have gone this way, or you could have gone this way, where we just like looked at each of the pieces of the t and computed those vectors directly. So I did it that way because plugging it into matrix vector equation, right? So I've written in these vector form because it's easy now for us to go back and say, we're going to plug it in. So we're going to say now this is our matrix vector. This is our linear system. We're using those. So again, I'll just mention that both of these, orange and green, used this proposed solution form. This is what an educated guess for what we think would be the right solution form. And we're trying to find the UV and lambda that will force this to satisfy this system, which is equivalent to satisfying this. So then we have everything. So the d vector x dt is this. And that is going to equal our A matrix. So I'll just grab the A matrix from up here. Or I'll just write A. We don't need to write the matrix. We'll just keep it shorthand. So we'll just say A. And then our what is our orange vector x is this. Okay, this is what we have to satisfy. Okay, immediately you can see that there is a e to lambda t vector v, e to lambda t vector v that are the same on both sides, so those cancel. Or actually, let's just say these cancel, the e to lambda t's cancel, because you can't really divide by a vector, but you could divide by e to lambda t. These are vectors, vector v, and so we can't. It's not as simple as just dividing those two out. So on this side, we have, once you cancel out e to lambda t and e to lambda t, which are just scalar expressions that you can divide, you have lambda v on this side, and on this side you have a lambda v. And people like to usually flip this around and just say it's a lambda v is equal to a vector v is equal to lambda vector v. And I want to point out here, A is a matrix. Okay, so I'll just label things. A is a matrix. Lambda is a constant. We said that, yeah. Lambda is some a to the lambda t, right? So it's not a matrix, not a vector, it's just a number. So we call that a scalar. So we have an equation that says the matrix times a vector is equal to some scalar times the same vector. So there has to be some special vector where this is true. You don't have to have taken linear algebra, but does this remind you of anything for anybody who's taken linear algebra? What does it remind you of? Yes, eigenvectors and eigenvalues. So in particular, this scalar lambda is what? Is the eigenvalue. And these v's are eigenvectors. Okay, so what happens is that, what did we do? We took this system, we rewrote it in a matrix vector form. We proposed that a good solution form for this appears to be u e to lambda t, v to e to lambda t, where the lambdas are the same because we need to make sure those exponentials end up being the same. Otherwise, we're not going to get everything on the right-hand side to have the same exponential as the left-hand side. The u and the v we still keep free. They can be whatever. But we're going to try to find the u and v constants that will force this thing to satisfy the differential equation. What do we always do when we have a proposed solution form? We plug it into our x and, well, in this case, not just our x, but both our x and y. And then we plug it into their derivatives. dx over dt and dy over dt. We're writing everything in matrix form just so that we don't have to write a lot and just keep it condensed like this. And then all we did was plug in our dx vector dt, our x vector, given our solution form, and then we notice that it's equivalent to solving this right here. This is it just reduces to an eigenvalue eigenvector problem for linear algebra, which you don't have to have taken. So we're gonna learn how to find the eigenvectors and eigenvalues. So there's a section in the book called Elementary Linear Algebra. It's in our textbook, so you don't have to open like a linear algebra textbook, although you can. But there is a section in there that reviews some linear algebra. So what's the point? We have to find our lambda as well as our vector v. Why do we need lambda and vector? A is known. A is like the A, B, C, D, which is the coefficient matrix. But the v vector and the lambda is not known. And the v vector contains u and v, which are the coefficients in front of the x and y, and the lambda is there. So really finding the eigenvector lambda and the eigenvector, which is the vector uv, is equivalent to solving for all three of these things. So once we find lambda and the eigenvector, then we would have found lambda, we would have found u, and we would have found v. And those go into these spots, and that's your xy solution to this differential equation, x of t and y solution. Okay, so let's take this equation we just wrote. Let's just copy this equation. And we're just going to solve this equation. And we're just going to keep it general for now, but like we'll have actual numbers in a moment. So what does this translate to? So we'll just rewrite this again. A vector, the A matrix is A, B, C, and D. The coefficients in front of x, y, they could be anything. The V vector is U, V, is equal to lambda, U, V. Okay. Let's do the matrix multiplication. So that's all really we need to do for the left-hand side is go left and then go down. So the left is going to become AU plus BV, CU plus DV. And then the lambda just can get multiplied to each of these. So it's going to be U, lambda U, lambda v. Okay. Let's write this as like we're just unwrapping this. This is the same as just copy this. This system of equations is equal to lambda u, lambda v. Okay, suppose you want to actually solve for this in general. One approach is if you wanted to eliminate, let's say, the v. So if you want to eliminate the v, then I'm going to, well, let's just do one more step. So I'm just going to say AU. I'm going to minus this. Oh, well, let's do this way. This is AU. I'm going to minus this lambda. So it's going to be A minus lambda U plus DV is equal to 0. And then I'm going to move this over. So it's going to be CU plus D minus lambda V is equal to 0. Okay. And now I just want to eliminate the v's. This is going to be easier to eliminate the v's than having it the other way. So the top I can multiply by d minus lambda. Because the bottom has d minus lambda. If I just can multiply the top by d minus lambda, then that one would also have that in front of the v. But the bottom needs to be multiplied by b. Now they're both going to have b d minus lambda multiplied to the v. And so we could subtract those two. So I'll just label the first equation as 1 and the second equation as 2. And if you wanted to eliminate v, the v variable, then it's possible if you just do 1 minus 2 after you've done these multiplications. So if you do 1 minus 2, you're going to have basically the V's will eliminate. So this is going to be B times D minus lambda, and this will be B minus, they're going to eliminate. 0 minus 0 is 0. So all you have are these two that are going to be subtracted from each other. The first, they both have U's. The first one is going to have A minus lambda, but then also this D minus lambda that's multiplied, minus BC, because the B times C times U is going to equal to 0. Right? So this will happen if you took these two and subtracted after you've multiplied those two. This can happen a couple ways. One way is if you let U just equal 0. Okay. If you make U equal to 0, then if you plug in U is equal to 0 right here, or in this first or second equation, really, it doesn't matter. If you plug in U is equal to 0 here, then this whole term is 0. You have BV is equal to 0. You'll get V is also equal to 0. Or you could plug it into this is be 0. And then the only way D minus lambda times V is equal to 0 is if you, I guess, you have no control over D. You can make lambda be D, I guess, but the other way would make B equal to 0. So this is called the trivial solution. I'll just say this is the trivial solution. If you make U equal to 0, then V will, this is equal to 0 too, and this is a trivial solution. Trivial solution is because it's the 0 solution. And if you do make U and V equal to 0, that will make X equal to 0 and Y equal to 0, because U is here and the V is here. Those being 0 make B 0. And if X and Y are 0, then you'll have 0 plus 0 and 0 plus 0. And what's the derivative of 0? It's 0. What's the derivative of 0? It's 0. It will satisfy this differential equation. The 0 will always satisfy this differential equation, but it's the trivial, it's not the interesting solution. We want the non-zero or so-called non-trivial solutions. The non-trivial solutions will only happen if you so there are two options, right? There's the either make this equal to 0, and the other option was to make this equal to 0. And it turns out that this either you have this or you have everything in here equal to 0. And this equaling to 0 will actually give you your non-trivial solutions. So I'll just say this condition will give you your non-trivial solutions. Okay, so that's basically it. So we're going to have to find lambda. This is an equation that only has lambda in it because we know our A matrix. That's like from the system of equations. We just read off the coefficients. So they're giving you that. So A, B, C, D are known. Lambda is the only variable here that we don't know. So we'll be able to solve for lambda because there's no U or V in this equation anymore. It's just an equation in lambda. It's a quadratic equation in lambda because if you multiply this out, you'll have up to lambda squared. So you may have up to 2 lambdas. And then for each of the, once you have your lambda, you can plug in the lambda into this equation, this system. So lambda, let's say lambda is 3, then this will be 3U and 3V. Well, now you've got two equations that have only two unknowns, U and V. So we got around from having 3 unknowns, but only 2 equations, right? We got around from that by noticing that given the structure of this equation, because it's an eigenvector eigenvalue equation, doing elimination gives you magically a condition on lambda that is purely a condition that has only lambda and things we know in it. So we could solve for this lambda. We may get multiple lambdas up to 2. And then each of those we can plug into this original system to find U and V. So then it ends up being that you might have 1 lambda. And with that, there is a corresponding U and V that satisfies this original system. And then there's another lambda. And then there's a corresponding U and V that satisfies the system with that lambda. And so, in general, you may have 2 lambdas because this is a quadratic equation in lambda, and quadratic equations can split into 2 distinct roots for lambda, 2 complex conjugate roots for lambda, or repeated for lambda. And each of those will go into this lambda here, and then we'll find a vector v, which is the u and v that corresponds to that eigenvector, and so eigenvalue. And so that's what we're going to do. So this is the equation that defines the eigenvalues, because this is the lambda, and we're going to use that to plug into the original system and find out the eigenvectors, which is the u and v, basically. People like to shorthand notice that this right here is the same as the determinant of, if you think about this, this is the determinant of a minus lambda b c d minus lambda. Based on the definition of determinant, it's just multiply these two, you get this minus multiplication of these two. So people say that write it this way is another way people write it. And another way people also write this is like this, which is the determinant of a minus lambda I. And I is the identity matrix. And these are all the same. So they're all equivalent. I'll write on this white space how this orange is equivalent to this. It's not that hard to show because you have the A and then lambda, and the I matrix is the identity matrix. So it's going to be 1, 0, 0, 1. So the lambda gets multiplied to each component. So lambda gets multiplied to this 1, 0, 0, 1. And then you're just doing A minus this lambda component-wise, and you just get this thing right here. So I'll write those, but they're all equivalent. So this is me writing. So this is our original thing we just found by hand at the very beginning. But this is equivalent to this, and that's actually equivalent to this. And the bold is signifying a matrix. And so these lambdas are called eigenvalues, and this equate all of these are equivalent. They call this the characteristic equation for the matrix A. It's actually quite nice that they call it the characteristic equation, because remember when we had just non-systems of differential equation, it was like e to the r, t to the rt, and then we found like a characteristic equation for r. This lambda is kind of behaving like our r, and we have a new equation that looks a little different than how we had back, and then it was ar squared plus br plus c is equal to 0. Now it's this a minus lambda times d minus lambda minus bc is equal to 0. But this lambda is kind of behaving like our r used to behave in the past. And so it's an equation that for just having a single differential equation, you read off a, b, and c from the coefficients of your x double prime, x prime, and x, and then you can translate that to a characteristic equation. For this one, you can look at your entries of your coefficient matrix A, B, C, and D, and then extract from that the characteristic equation for lambda. So the name kind of works together with that. And of course, these are the eigenvalues of this matrix. So these are the lambdas. Okay. Oh, come on. It's lambdas. Okay, so in the end, you're going to use this characteristic equation for the matrix A to find the eigenvalues. So that's like find the eigenvalues lambda, satisfy the characteristic. For each eigenvalue, you plug it into the original system of equations, which can be written in this condensed form, to find the u and v that are components of your vector v, which is called the eigenvector. So once you find a lambda, then you could plug it into your system of two equations, and you'd only have two unknowns at that point because lambda is not an unknown anymore. And so you can find your u and v. So let's do that this is not like, this is just a practice, because, we're going to use this technique to find the equation of the solution of a differential equation. But let's just practice. So how does it work? You're going to first use the characteristic equation, which is like the a minus lambda times d minus lambda minus bc is equal to 0, with these being your entries for a and b, c and d. So you'll have 4 minus lambda. D is 0, so it's going to be 0 minus lambda. Minus the b is -3 times 1 is equal to 0. This, if you multiply it out, ends up becoming lambda squared minus 4 lambda plus 3 is equal to 0. And this factors lambda minus 1, lambda plus minus 3 equal to 0. So your lambdas are equal to 1 and 3. They're two eigenvalues. For each of those eigenvalues, we could plug it into our original system. So I'll just say for lambda 1 is equal to 1. What is our original system of equations? The eigenvalue eigenvector equation was this, which we can expand out. So what is our A matrix? Our A matrix this for -3 and B. And then let's translate this to B for U minus 3V equals to U, because this is 1 times U. And then the last, get U minus 0 is equal to V. Okay, so we have two equations for two unknowns, but it turns out that they're equivalent if you think about the first one. So if you took the first one, and let's say you moved this to the other side, so you get 3u, which is the equivalent to v has to equal u. But what is this equation? This equation is u is equal to v. So they're both the same. They give you a relationship. They basically say they have to be the same, but they don't actually give you an exact value for both of them. So it does give you some information, but it doesn't. This is written like this. So if you look at u and equals v, u is equal to v. Well, let's say v can be anything. So say v is arbitrary. So we'll just say it doesn't give us that v has anything in particular. So we'll just say v is equal to c1. Well, both these equations are the same, and once v is equal to c1, then u must also equal c1. It just says that v could be whatever, but whatever it is, u better be the same as that because u is equal to v. And so there's still one degree freedom built into this. So this gives us our u and v. So our vector explaining this as because it's our eigen, but we just said that there if we could factor out the c1 and you get c1 times 1, 1. And this is the eigenvector for lambda 1 is equal to 1. For the other one, it's a similar process. So lambda 2 is equal to 3. You're going to build the same. I'm going to copy all of this because it's exactly the same equation with only one thing that's changed. This right here becomes a 3. So then you're going to still have this system v on the side. And then you can again notice that they're both the same equation. So if you actually let's say you move this 3u to this side, then you'll have u, and then move this to this side is equal to 3v. And obviously this is the same as u is equal to 3v as well. So these are the same. They always end up being the same. So you can say, again, let's say v is arbitrary. Well, if v is whatever, then u better be equal to 3 times that. So this gives you a relationship between u and v, but it doesn't explicitly say u is something or v is something. So you have the freedom to say, okay, well, v can be a free variable, basically. But then once v is a free variable, u is fixed to be 3 times that. And so our eigenvector for our for the second eigenvector is going to be this. I'll label this as 2. So it turns out that one of them will always be free. And it's going to be like, let's say v is equal to C2, then u better be 3C2. You can draw out a C2 and just 3 and 1. And this is the eigenvector for lambda 2 is equal to 3. Okay, so that's how you find your lambda as well as your vector v's. Okay, so you have 2 lambdas, and each of them has a different corresponding eigenvector, which is describing a vector up to a constant. C1 and C2 can be arbitrary constants. Okay, how does this connect to solving a differential equation? So let's look at this one. The book, this is just from the book, but like we should be able to rewrite, so I'm just going on top of each other, you get dx over dt is equal to 5 x minus 4y. dy over dt is equal to 2x plus y. We just need to extract the coefficient matrix. Coefficient matrix is going to equal -5. We have our eigenvalue equation, which is this thing. Okay. Times d is 1 minus lambda times minus bc, which is going to be 2 times 4, but that's negative. But then it's going to be, so it's plus 8 is equal to 0. And this ends up becoming lambda squared plus 4 lambda plus 3 is equal to 0, which is the same as lambda plus 1 lambda plus 3 is equal to 0. So you'll get that lambda is equal to -1 and -3. Those are your 2 eigenvalues. And then we do this whole, okay, so for one of them, lambda 1 is equal to -1. You're going to say my matrix, my eigenvector equation is this. And for our current one, our A matrix is -5, -4, 2, 1. Our vector is UV. Our lambda is -1, right? So this is like -1. So -1 times UV translated to an equation will end up being -5u plus or -4v is equal to -u. And then 2u plus v is equal to -v. They're both going to be the same. So I'll just use the first one. You can check on your own that they'll be the same. So the first one, if you move this -u to this side, it'd be -4u minus 4v is equal to 0. Actually, let's move the 4v to the other side. So let's just say this is equal to 4v. Positive 4v. And then you could divide both sides, and then you'll just get that u is equal to -v. So then if we say that V can be anything, is free, let's say V is C1, then U better be negative C1. So that gives us our eigenvector. Again, eigenvector is built off of the U and V. It's going to be negative C1 and C1. So it's going to be C1 with a negative 1 and 1. This is going to be the eigenvector for the lambda is equal to negative 1. All right. For the other one, we have the same exact stuff. So I'm just going to literally copy all of that. Only one thing changes. This negative 1 becomes negative 3. Which means that on this side, it's going to be negative 3u and negative 3v. We could use any of these. They're going to be the same. So I'll just use the second one. If you use the second one, it'll be 2u. I'm going to move this v to this side. So it's going to be negative 3 minus the v, so it'd be negative 4v. Divide. So u is going to equal negative 2v. So again, v can be some free variable c2. And I'm making the free variable in general may not be the same. C1 for the lambda 1, C2 for the lambda 2 is going to mean that the u has to equal negative 2c2. So our eigenvector for our second eigenvalue is, again, this u and v. And it's going to equal negative C2, C2, factor out the C2. So it's going to be negative 2, 1. And this is for lambda 2 is equal to negative 3. Okay. All right. How does this connect to the solution of our differential equation? So look, this was our whole point of doing this is we just found lambdas and u and v's. There are multiple lambdas and there are multiple u's and v's, but this is going to be our solution form. So recall this. I'll just copy that down here. So we can do this. So recall solution forms x is equal to, so x of t is equal to u, e to the lambda t, and y of t is equal to v, e to the lambda t. Okay, so this is not unlike what we saw before where we had two distinct roots, right? So we've only had two distinct, well, what do I mean by two distinct roots? The lambda, the eigenvalues are two distinct roots. You have a quadratic equation of lambda, and I've written all these so far so that there'll be two distinct roots. In general, they may be two complex conjugate pairs or repeated. And we'll look at those. Actually, we're not looking at the repeated. We'll just look at the complex conjugate because I just need to abridge a little bit. But for distinct real, remember back then when we had two distinct real for R, we had one homogeneous solution and we added the other homogeneous solution, right? Same idea here. We have two distinct lambdas. For this one of them was -1 and the other one was -3. So for -1, we had the u was equal to negative C1. So we'll just write it like that. So we'll say it's going to be u was negative C1 whenever lambda was -1. That's the first. So if you're trying to say lambda is equal to -1, that means we're plugging a -1 into this lambda right here. And then we're going to say, okay, lambda is going to be -1. We're going to read off what the u was. So that's negative C1. And then that's for the first one, lambda is equal to -3. Lambda is -2c2. So I'll just write -2c2 e to the lambda. We're just plugging it into the spots, but there's two lambdas. it's like two homogeneous solutions. So we're just going to add them up together. The same idea for y. The y is going to be the v. V was just C1 when lambda was equal to -1. So it'd be C1 e to the negative t. Plus the other one was for when lambda was equal to -3. Our C2 was just C2. So it'd be C2 e to the -3t. So this is the solution for when lambda was equal to lambda 1 was equal to -1. Same idea with this one. This was the solution for lambda was equal to -3. Same idea with this one. Okay, so these turn out to be, if you plug in this into our system right here, this blue stuff right here, if you plugged in that x and that y into here, and then their derivatives on the left-hand side, you should get both these equations to be satisfied simultaneously. Okay, so that's how you connect the eigenvalues and eigenvectors into a solution for the differential equation. But a lot of people also like to write this in vector form. So the solution vector x is a function of t, is built off your x and y. And this is the same as people like to say it's e to the lambda 1t, where this is like your first eigenvalue times its corresponding eigenvector plus e to the lambda 2t times its corresponding eigenvector. And let's just say, confirm that this would give us the same thing. So lambda 1 was -1, so it'll be negative e to lambda e to the negative t. What is vector, eigenvector 1? The first eigenvector was c1 times -1 over 1. So it's going to be times c1, -1, 1, plus e to the -3t. And what was the second eigenvector? It was c2 times this vector. So it's going to be c2 times -2, 1. And if you were to multiply this out, this e to the lambda t, e to the negative t times c1, these are just some expression that you can just multiply to the top as well as the second. So it's going to be equal to, so I'll write it, so I'll just write it out. Yeah, so it's going to be c1, so it'd be negative c1 e to the negative t. And then this one is going to be -2 c2 e to the negative t. And then the bottom one is going to be c1 e to the negative t. It's going to be plus c2 e to the negative 3t. This is if you were to take each of these, like e to the negative t times c1 times the -1 is this. This one is like this multiplied by this one. And if you check, right, this is supposed to be your x and your y. It should be the same. So I'll just circle and say. Does that look the same? Yeah. So some people like to write it like in this form. So if you like to write it in vector form, you could just write it like this. You could just write it like this if you want, where you just say e to the lambda 1t times vector v1 plus e to the lambda 2t times vector 2. That's, I think, easier than trying to read the u and the v and all this stuff. You could just write it like this. And so that's the punchline for distinct real eigenvalues. The solution to this matrix equation is like finding the eigenvalues and eigenvectors and then putting it in this formula. Okay. So we'll do that. Yeah, we'll continue next. Thank you. See ya.
It'll be too close because I won't have probably
Reed's theorem. Well, it's just going to cancel the 0 off the top. So it's very.
I had a question on that one too.
Okay. So the x1 PQ. So
These are what I have.
Yeah, they look right. And then you're just doing x2. I mean, these are not the same because this is s cubed, whereas this is t cubed. They're like they're different.
Oh my god.
And so when you take the interval, the t is actually like our is not from the perspective of you're taking the interval with respect to s. The t is not involved. It's almost like acts like a constant.
Okay.
And then s is the actual variable.
Yeah, I had a question too, because I put it into Wolfram Alpha and I was not getting the same answer. This is what eventually I got. And these two are the same. I know like these are right, but it's just these two terms that I got confused with.
It's fine because those are just if you think about it,
Oh, sorry.
those are this is like a half times t cubed, which can get absorbed into the C2.
Oh,
And
okay.
this is like negative half times t, which can get absorbed into the C1.
Okay, so because I was like, okay, well, this technically would be a number, and then these are just
Oh,
the
because the
same.
Wolfram Alpha probably
Yeah.
just had this
Yeah.
plus this, right?
Yeah.
Okay, so that means you did everything correct, but these actually absorb into these constants because this is t cubed, and this is just like
Oh, okay.
half times ct cubed. So C2 times a half is still another arbitrary constant.
Okay.
And so they gotta get absorbed. And the Wolfram will, absorb these because they will be smart.
Okay, that was driving me nuts. I spent like 2 hours on it trying to figure out
Oh,
what I
not
was doing.
2 hours, those are 2
Yeah.
hours.
Then I was also confused on 3.1, the linearly independent solution. So
Good.
it's the fundamental set. but
Because
then
it
it's-
doesn't equal 0.
Yes.
That's all.
Is it, do you go further than that or no?
No, that's it.
Oh, that's it? Okay.
Yeah. So, if your Wronskian is non-zero, then you're definitely linearly independent. There's the weird case where if your Wronskian is equal to 0, you may still be able to show that it's linearly independent, but like, yeah, that one's a weird case. But if your Wronskian is non-zero, then you're for sure guaranteed that your set is linearly independent. And actually, the fundamental set requires the Wronskian to be non-zero is a stronger condition than the linear independence condition because you can have solutions that are linearly independent but not their Wronskian is equal to 0. But you need Wronskian is non-zero for you to be able to solve any general initial value problem.
And then similarly here, like I understand T naught, so it's not 0 at time at the initial time, so it will always be non-zero. So they're linearly independent.
That's good.
But then it's saying for the second part,
Yes.
X3 is linear.
No.
Dependent?
X3, you should be able to find an X3. What did they ask? Show that you
It's
can
like
find
it's like
X3
multiplied by
is
an
equal to
alpha
alpha X1 and then plus
Beta
beta X2.
So
So the fact that you just showed that X1 and X2 are a fundamental set means that that means there are two linearly independent basis vectors for the space of the solutions. So that means that X3 should be possible to write as a linear combination of those two. So you should be able to say
Okay.
C1 X1 plus C2 X2. And then you just have to find C1 and C2 that satisfies those initial conditions. They give you like X of 3 at T naught is equal to alpha and X of 3 at X of 3 prime at T naught is equal to beta. You got to plug those initial conditions, apply those initial conditions to find C1 and C2. And you should be able to get that C1 must be alpha and C2 must be beta. And therefore you've shown that given this X1 and X2 that are built off of those initial conditions, any linear combination of any other solution with other arbitrary, that's why they use alpha and beta, because they could be anything, can be described as a linear combination in that precise way, alpha X1 plus beta X2. And so this proves that a fundamental set always exists because you can build X1 and X2 the way they did, and then any solution can be, for any initial value problem, can be written as a linear combination with your initial condition on the function and its initial condition on the derivative is satisfied like that.
Okay.
Yeah.
Right. That's very helpful because like I understood like well at least I thought I did. I just need to be sure about just the fact that there are the fundamental set. It can be those alpha and beta because they don't tell you what it is, or entirely be anything that's a combination of X1 and X2.
Yeah, so like there's like it's like saying like you've got your two X1 and X2s. They're a fundamental set. I mean, there could be other fundamental sets, but
Yeah,
I mean, if you have those two, then some other solution X3 that you're trying to find that satisfies the differential equation with some arbitrary initial conditions for it on itself as well as its derivative can always be described as a combination of X2 and X1 or X1 and X2 with appropriate coefficients in the front. That's the idea, is that like get to any other solution by some linear combination of your two fundamental solutions. And that's great because then all you need is those two fundamental solutions with C1 and C2 multiplied to them, added together. That does indeed describe all possible solutions. If your X1, X2 happen to be not a fundamental set where they're not like linearly independent from each other, then they'd be constant multiples of each other, and you're gonna not be able to always satisfy. You know, you're not gonna always find all. It's not gonna capture all the solutions
yes,
in general.
just
Like one dimension of the solution. So there's a two-dimensional space basically, but you've only, so it's almost like saying if you're in a or XY coordinate plane, you need you need,
don't, so you're saying like if they're dependent, then it's like you still only have the X axis.
Yes.
If they're independent, you can have the X.
yes,
axis.
exactly.
Got it.
You could actually have two vector, you know, the canonical basis set for XY plane is the 1, 0 vector and the 0, 1 vector.
Mhm.
You could actually have two vectors that are not like they don't have to be like perpendicular like that. You could have them like this basically.
Yeah.
And linear combination of those two will still get you somewhere,
To X,
anywhere on the XY plane. You need them to be like not on top of each other.
yes.
So if they're both constant multiples of each other, so you have a vector that's 1, 0 and then a
point the
2,
exact
0,
same-
they
yes.
point in the same direction. 1, 0 and 2, 0 are linearly dependent because they're constant multiples of each other.
Yeah.
And
one
so that,
times two gives-
yeah, exactly. So if you had, it's like, this is a more complicated because it's a space of differential equations, but if we were to project this onto a R2 plane, which is the XY coordinate plane, it's equivalent to saying you have two homogeneous solutions that are constant multiples, would be the same as saying I have 1, 0 and 2, 0. To try to describe all points in XY plane, it's not sufficient to do a combination of 1, 0 and 2 zeros. You need them to be linearly dependent, which means not constant multiples of each other. That will allow you to have combinations of the two vectors that will allow you to describe any point in the XY plane. Similarly, for differential equations, you need two homogeneous solutions are kind of your basis vectors, and you need those to be linearly independent so that linear combinations can get you to any of the infinitely many differential equation solutions in the space there. It's that space is like basically it's a two-dimensional space as well because you only have two vectors.
Mhm.
It's not like your traditional vector like 1, 0 and
Yeah.
0, 1. It's like your vector is a function,
Mhm.
and the combinations of two of these different linearly independent functions give you another function that's in the space of all the solutions that are described by that are spanned by these two basis vectors, just like 0, 1 and 1, 0 span the space of R2 is basically the real number plane.
Yeah.
The R3 would need three vectors, X, Y, and Z axes.
In R3, can you have an X1 and X2 that are only two-dimensional, but an X3 that's three-dimensional still like?
Yeah, you can,
Okay.
you can. So that's fine. So that's I mean, it's like two dimension. It looks like two dimensions because you can set the normal canonical X direction and the Y direction, and they both be on a plane.
Mhm.
So you're like, it looks like 2D, but you have to kind of think of it as actually a plane sitting in three-dimensional space.
Yeah.
But it is equivalent to like a two-dimensional plane that just happens to be sitting in a three-dimensional space. So our solutions, the fundamental set having two like homogeneous solutions that are linearly independent, combinations of them will get you to any of the infinitely many solutions, but it's still like a space that's has the same size, or I mean it's equivalent to like you know, 0, 1, 1, 0 kind of. So those spaces are like what one would call like isomorphic. They're basically the same. But in terms of the degrees of freedom and the structure and the dimensions, they're the same, but they're kind of different because one's actually vectors, one's actually the functions are actually vector acting like vectors.
Okay.
And so if you can confirm that you have two x1 and x2 that are not constant multiples of each other, then any solution can be written as a linear combination of those two. If one of them happens to be a constant multiple, then it's kind of redundant because they're already being multiplied by arbitrary constants. So you'll have like C1 times X1 plus C2 times X2, but X1 and X2 are themselves constant multiples of each other. Then you could just combine them and just have only one solution in the end anyway. So you do need X1, X2 so that you can't do that. They're actually linearly independent. Then then everything we've done, you could check there, you know, for the domain of where the domain of where the differential equation is defined, they will always have a Wronskian that's non-zero, and therefore they will be linearly independent. So we've been doing that when we find x1, x2 all along, but it's good to point it out so people know. Yeah, that's kind of it. So you haven't taken linear algebra, but
No, I will be taking it next semester.
yeah, but you'll see a little bit more about like what these all mean and stuff. And in you know, eigenvectors and eigenvalues is also what's usually they cover it towards the end. So some people who are in linear algebra now are probably seeing it right now.
Okay.
So they're kind of like noticing that well, I'm covering it, and then they're also covering it. So they're just kind of like sitting here like, okay, we're just getting the same thing. But then you'll see it again when you take linear algebra.
Okay. Well, thank you.
Yeah.
Yeah, I'm contemplating, well, I probably will, but I'm contemplating adding a math minor.
Usually you can do that
So I'm like, I will be one class short of it after linear
after the
algebra.
algebra.
But for my last class, I'm not sure what I want it to be.
Yeah.
There's I think I saw dynamical
Systems. Yeah.
I think it's like 4325.
Yeah, that would work.
And that's kind of just like a progression directly on.
Yeah, I would
this.
say that builds off of our class and moves on from our class. It will be mostly like, so the systems of differential equations that we're doing now is probably where it will start. Like it will probably like look at systems of equations right away.
Okay.
And then they'll maybe have because our systems are actually homogeneous if you like rearrange it. They may look at non-homogeneous, they may look at non-linear as well. So our systems have x and y, and their derivatives are all to a power of 1. So they'll do other things like that. And then they'll try to graph and plot these solutions on a phase plane. But we'll do that with these equations as well. So if you like kind of differential equations, and then it's probably going to blend it with linear algebra, then that would be a natural next class. So there are other people who took my MyDiffEq who enjoyed that kind of stuff, so moved into that class. There's also mathematical biology, which also uses differential equations, but it would be like kind of dynamical systems as well, but specifically for biological applications. So some people enjoy just, and maybe if you're like, I don't think you're pre-med, but like some people might be pre-med and they're like trying to, apply math to biology. That's like, interestingly, you can't take mathematical biology until you've gone through differential equations and linear algebra, I believe. So it's a big commitment for a pre-med person to be like, I want to take mathematical biology, just because they want to see how math could get applied to like cell cycles or epidemiology and disease outbreaks and other systems, biological systems. But if somebody was really ambitious, they probably would minor in math at that point as well as be pre-med, and then mathematical biology would be an obvious choice for that, which uses similar things like we're doing but applied to biology. Dynamical systems is more general, so like it'll use stuff that we learned, and it'll maybe more like theory behind it, and then applied to not just biology. They may have like examples that apply it to biology, but it might be also like business, which is like what you're interested and
then so
other things.
finance, because one way to just finance my other is physics.
Physics,
So
yeah.
then-
And other physics applications.
Yeah.
That like physics shows up everywhere. So dynamical systems will probably look at like applying differential equations, systems of differential equations to describe like different physics systems, physical
Yeah.
systems, like the pendulum or whatever.
Mhm.
Depends on who's teaching it and how they want to incorporate it. So I think it's a more maybe general one, and so probably better for somebody who's not just biology. Yeah, I think you're so close to it, so it might as well. I mean, you're already taking, guessing you're taking, does physics need linear algebra and diffie-q or just,
Technically, it doesn't need linear algebra
That's
for
what I
some
thought.
reason, but it should.
Yeah.
But for one of the courses at least I'm interested in taking, I do need to take dynamical systems.
oh, okay, well then,
So, that's why I was just curious.
oh, okay, yeah.
Um,
For physics, you need there's a class that needs dynamical systems.
There's one,
See.
yes.
Okay, so it's a big, like, people could avoid taking that, I guess, and still
Yeah,
get
yeah,
the
there's-
physics
there's-
major.
there's Plenty of different
Oh,
electives you
okay.
can go down, but that's
Which
just
class
one
does that?
I'm trying to remember, it might be, I believe it's something with thermodynamics.
Okay. Okay, yeah, so because like essentially anybody who wants to take that physics class will have to minor in math at that
Yeah.
point, because they're gonna have to take diffie-q and linear algebra
Mhm.
and dynamical systems.
Yeah, it's, they're kind of like, I think they're just trying to encourage people to like get into the things.
I think it's-
So it's like
yeah.
there's a lot of math already.
Yeah,
And I think the dynamical systems class as well counts as one of my physics electives that, so.
okay, so then you can double dip on that as
Yeah.
well. So it's like you're using it as a prereq to this other physics class, but it itself can be counted as a physics elective, then
Yeah.
basically it's not wasting your time.
Yeah,
Yeah, I mean, that sounds great. And you're also finance. I mean, you're probably gonna be amazing if you're are you trying to be more in finance later or physics? Okay,
Finance,
so if you're
yeah.
trying to get into
like quantitative
finance,
most likely,
yeah,
so.
then you're gonna stand out a lot. I mean, because you have these other degrees that are very rigorous, I would say, like probably more difficult than the finance. Both the math minor and the physics will probably be no judging like the finance majors, but I would say like
My finance course right now, like super expensive, like comparatively, because.
this class is, I mean, you're doing so well in this class that this class might also be super easy to you, but like comparatively,
Not like, this is probably like my hardest class, in
Okay.
addition to physics this semester for sure, but,
okay, so you're
I
doing
feel like
really
I'm
well
equal.
between physics and this class. I see. So it's not an easy class. It's harder than your finance classes. So imagine all the finance peers that you have who are not doing this. I mean, it's like on one hand, you're like, why am I killing myself? But on the other hand, you'll get really appreciated later. I think it will like it will.
I mean, I enjoy it, I don't.
Yeah, and if you enjoy it, then yeah, it's not like you're killing yourself, you're enjoying it.
Yeah.
So I mean, it would be killing yourself, I guess, if you really are hating it, then maybe it's not
If I
worth
was
it.
in, like an English minor, that would be the case.
Then you'd hate it, yeah. But if you're enjoying it, then that's great. It takes up a little bit more of your time and energy. But if it's very good for you, I mean, it's very like at the end of the day, you reap what you sow. Like if you end
Yeah.
up putting in the work and developing yourself, it will get recognized. If you're applying for the same position, you've got two candidates and someone's got these extra things going on. They really like that, I think. I mean, not that I'm in that field, but they probably will really they actually like I've heard that like they don't even like they may even like not care if you had a finance major. There's like some people who just have
Yeah.
straight up math physics double majors, right? So like if you doubled, I mean, you probably can't double in math and physics
No,
because
it's
of
just-
the finance.
It's just too many.
Yeah.
questions.
Yeah, but you might have been able to if you like dropped your finance major.
Oh, yeah, for sure.
Then you could have done the math physics double. And those people will probably look even better than just the finance single
Mhm.
major,
Yeah.
You have the finance and the physics and the math minor, and that blend is probably also really, really attractive. So, you know, so it's really, they like that. I think they really like the physics, math stuff. But really good job on your, I mean, I think test two was, like I said, probably the easiest of the three tests, because it was just kind of like the method of undetermined coefficients.
Yeah.
The next test will be like, you know, we've done reduction in the span of maybe a couple weeks. We're doing so many things.
I understand, like, I understand, Framers, which was using the Rotskin
Mhm.
alone really well.
Mhm.
It's just, like I said, I don't know why I confused myself with the green.
The Green's function is a little trickier,
And
yeah.
This is definitely harder, but I just need to like sit down with it like this weekend and like just really grasp.
Yeah, yeah. There's just more, I feel like there's more variety that we're covering now.
Mhm.
Whereas like the second test, it was just like second order equations and just like only that, and it was pretty contained. But now we're like touching on linear algebra, a little bit of this, a little bit of that. Like it's like a lot more, and everything is each of those things end up being a little more work and involved. So, uh, so you know, just you'll be fine if you just do it.
Yeah.
I think yeah, we had like. We had like 500s on the second test. And I think you were one of them. So,
Yeah,
did you have like a physics class you're missing right now? You shouldn't.
no, I'm just gonna go to the dining hall right now before they start